Okay, so let's continue on the lecture. We were looking at parametric equation, and there is a question in assignments. Okay, I'll give you a similar example as the question in assignments there. Okay, so. Okay, so this is basically a roller coaster parametric equation. Okay, so everybody loves roller coaster. Okay, if you go to Disneyland, just can't have enough of that. So, what are the math behind this roller coaster here? Not all of them, but part of the work probably could be this. This is actually so-called a 3D Lizardo curve. If you're going to, if you're using also a scope, okay? So when you connect x and y with the sine and cosine, and chances are you'll see these so-called Lizardo curves here, okay? So now the question here is, what would be the velocity of this roller coaster? So this is the trajectory, then at any point on the roller coaster, what's the velocity essentially, right? If you can calculate that, you know pretty good where you should get prepared if those high velocities coming up. Okay? Yeah. So in this question here, r of t equal to sine, this is s of t, 2s of t, cosine s of t, and s is a function of t. So in assignments we use the theta, but it really doesn't matter. So there's an intermediate variable over here, right? So s over here could represent arc length or the displacement along the roller coaster. Okay? So then when we do the velocity, we know that velocity, okay, equal dr over dt, right? Okay. So, but r, okay, is a function of s, then is a function of t. So in this case, we actually need to use a so-called chain rule. So dr over ds first, and then ds over dt. Okay. So this way, we can calculate this dr over dt, the velocity. Okay. So the rest of the job is actually pretty simple now, because r has 3 components here. So I need to calculate this first. Okay. And then for this guy here, this guy here, ds over dt, we don't know what the ds over dt is. Basically, the question didn't give us what the velocity is. So what we'll do is we will simply leave this one as it is. Okay. So as you remember, we also can write this one as s dot. Okay. So s dot is essentially Newton's notation for derivative times derivative. Okay. So dr over ds, so we look at it separately, each one of the component here. So let's look at dx over ds first. Right, this is dx, right, this is x over ds. Okay? Yeah, so simple derivative, right? Yeah. So dx over ds, that's sine s of t, so that's just basically cosine s here, right? That's basically cosine s. Okay? Is that good? Yeah. So technically, I can also write this. So this dx over ds. This dr over dt, I'm actually looking at as the dx over dt over dt, and which equal to dx over ds and ds over dt, right? More specifically. Okay. Yeah. So that equal to what? Cosine s times this s dot. Okay, times s dot. So we leave it as it is, okay? Yeah. So that's dx over dt. And then you calculate the rest of the two here. Okay? This is actually not bad. In case you have a bit of a long expression, so you just got to be careful here. So for example, this one sine 2s, right? Sine 2s. So in terms of this one, this is basically dy over ds and ds over dt. Okay. And y is what? Is sine 2s, okay, and s dot. Okay, s dot. Okay. So if you want to introduce another chain rule here, basically you let u equal to sine 2s, and that will be du over ds first, and then sorry, sine u, d sine u over du, and then du over ds, right? So this is basically what? 2 cosine 2s, right? And then s dot. Was that okay? Yeah. Okay. So the last one, and dz over dt over dt. And what's the dz? Z is cosine s, so that's actually pretty simple. Okay. So dz over ds, it's just the derivative cosine and becomes negative sine, and s dot. Okay, s dot. Okay. So this is the derivative of each one of the components, right, of that position vector r of t, and altogether your velocity, okay, is basically this one cosine s dot plus that guy 2 cosine s 2 cosine 2s s dot plus minus sine s dot and t hat. Okay, yeah. So that's velocity. So you can apply a similar approach to the assignments there, okay, for this particular question, okay, this kind of question. Okay, any questions? Yeah.
So in the final product here, you're describing as cos of s and cos of t. Would it still be okay to describe it as cos of s of t or cos of 2s of t?
Oh, doesn't matter. Yeah. So actually, you can put a bracket of t, no problem at all. But if you don't put it there, when you see s dot, that actually naturally you see that that's a function of t. Yeah. Because when you use s dot, this notation, that's basically general convention. That's a time derivative. Yeah. This is a time derivative. Okay. So you don't use s dot to indicate. I mean, if it's a ds over dx, for example, you don't write it as s dot. Okay. And only when this one here, you write it as a ds as s dot. Okay. That's sort of notation here, time derivative. Okay. So that should be it for operations regarding vector functions. All right. Derivative and integrals. In the lecture notes, I also include a little optional ones as the curvatures of the curve. This radius, the curvature. What's the meaning of that? So you can take a look at that. Just only 2 pages. Pretty simple. Okay. Yeah. So now let's continue and let's look at a new concept now. Okay. So we look at the so-called arc length, okay, and a new concept called scalar line integral. Okay. All right. So I'll explain what this is. Okay. But let's look at the arc length first. So we're going to make use of the vector functions. Okay. Yeah. So first it's arc length. The name pretty much explains itself. If I have a curve in 3D space, okay, so the objective is, let's just say the curve starting from here and ends at here. Maybe this is at the t equal to t1, at the t equal to t2. The time moments like this, right? Yeah. Then we might have a point P1 at the t1. And there's probably another point P2 at T2. Okay, yeah. So overall, you have this curve can be represented using a vector function right? R of t. Okay, so vector function R of t. That's the vector function for this curve. Okay, so the question is, okay, what's the arc length, right, between this t equal to t1 and t equal to t2? Basically, how long is it this string is? Okay, of course you're going to fully extend it, and that's how you measure the length of that, right? The total length. Okay, that's what we call the arc length. Okay, yeah. So here's the objective. Okay, in plain words, basically how long, right? It is, okay, from t equal to t1 to t equal to t2. Okay. Okay, so this is how we approach this kind of question right here. Okay, so how we could approach this. And what I'm going to do is I'm going to use some approximations first. So I'll pick, okay, 2 points, okay, on the curve. Let's say this is A point and this is B point. Okay, yeah. So then for the A point, you have a position vector for the A. For the B, you also have a position vector here, right? Yeah. Then between A and B, you can construct another position vector, okay, like this, between A and B. Okay, so 3 vectors, a triangle like this, right? Yeah. And if I label the vectors each at here, so this is A, maybe I'll label it R of TA, okay, at the t equal to TA, we are at this location A. At t equal to TB, it's at location B. Yeah. Okay, so if the question here is asking is what's the arc length between A and B location, right? The arc length between A and B location. Then based on the drawing I just made it here, I can use an approximation, right? To approximate this arc length, I can use what? I can use the length of AB, right? To approximate the arc length AB. Make sense? Yeah, so basically, if we're saying what's the arc length, I'll use S for arc length, okay, between AB, it's approximately the vector, right, the vector AB there, okay, the vector AB, okay. So I'm gonna basically, for the arc length AB, okay, I'll say it's a delta S. Okay, it's a small arc length. Okay, delta S at here. So the question is, what is the vector AB? Sorry, should be absolute value, right? We're talking about the scalar quantity. Okay, not a vector. So what's the quantity for this one at here? Right. So based on this, diagram here, it's actually what? Vector AB is this vector subtract this vector, right? Yeah. So that's R vector TB subtract R vector TA. Okay. Okay? Yeah. Okay. So that gives us this vector AB at here, right? That gives us a vector AB. Okay, so now I'm gonna give it another name here. I'll call it, okay, I'll call it a delta R. Okay, I'll call it delta R. So good. So delta R. So delta R. This one means this is the absolute value of this delta R vector, and I'll write it a little bit redundantly. I'll write it like this. So remember, when you're talking about the magnitude of a vector, we can use dot product. So this dot to this, right? Then you take square root, that gives you back the magnitude. Okay? So this step here seems to be redundant, but it will lead us to a formula that we're looking for. Okay? Yeah. Is that good? Yeah. So now, to be more redundant, I'm going to divide this guy with delta t. I'm going to divide this guy with delta t. Okay? So basically, I'm modifying this one here. I'm dividing delta t here. What did I add? I add a kind of like a 1 over delta t squared here, right? And if you have this square root 1 over delta t squared, and that equal to 1 over delta t. Okay? But you can't change this, right? You can't modify this one here. So this one has to be the same as this. So in order to keep these two as equal, so what do I have to do? I have to multiply this one with delta t. Okay? So this way, I'm not changing it, right? I'm not changing it. Okay? Just modifying it. Manipulate to what I want. Was that good?
Is that inside the square root?
You mean this square? No.
Is it inside the square root?
No, not inside, outside. Yeah, so like this. Okay? Can you get this? Yeah. Right. This is very clear. You know, this is a over a times a dot b over c squared, right? And that basically 1 over c a dot b. But you can't change this, so you times c. See, right? Okay. Yeah. Okay. So now let's look at together here. So this is a delta s equal to this, right? Equal to this. Why do I put a delta sign here? Because you see, imagine this, right? If the TB is very, very, very close to TA, okay, very, very close to TA, that delta sign actually becomes what? Becomes, in the limit concept, becomes the delta changed to D, right? The delta changed to the D, okay? Infinitesimal small quantity, okay? That's the delta. So, what this means basically, okay, this means ds, okay, you change this delta sign to d, so ds equal to, okay, over here, dr over dt and dot dr over dt and times dt, okay, times dt. Does that make sense? Yeah? Right, that's a good approximation, right? Yeah. So we're not skipping any steps here. Now, back to this arc length. Now remember what ds represent. ds represent, it's the arc length of an infinitesimal small quantity, right? But what you need is, you need the arc length for the total arc, for the total curve. So, then the total arc length, so see total. So the total arc length, instead of s now, instead of ds now, it's the s we're looking for, right? It's s we're looking for. So s equal to what? Equal to the integral, right? Integration of all the ds together. Where do you do the integral? You integrate, right, between the t1 and the t2 that you're looking for. Okay, that's this arc length. So we have ds over here, then just simply plug this into this integral here. Okay, there, right? This is a formula for arc length. Okay, yeah. So if you look at the formula here, that might seem to be pretty strange here, but it's actually, it's not bad. Because why? It's because, okay, there's a dot product. Dot product gives us what? Scalar quantity, right? Scalar. Okay? So that's exactly what you're going to have as arc length here. Yeah, then there's a square root that you need to carry out though, okay? The question is basically, as long as you have this r of t, right? As long as you have the vector function r, you can always take a derivative, and then you can always do the dot product, right? So it's doable now, okay? Sometimes we write it, okay, use a different notation here. So inside here we use prime, okay? Just remember this is basically the same thing, okay? The same thing. More frequently, because we know that, okay, we know that r of t, okay, is represented using the three function x of t, y of t, z of t. So guess what? If you plug this one, okay, if you plug this one into this formula, okay, let's just say what do we get in terms of x of t, y of t, z of t. Okay, you plug it into it. So take derivatives first. You get dx over dt, dy over dt, dz over dt. And then do the dot product. Then you take the square root, right? Take square root. So you're going to end up with this one here. Okay, square root. Okay, that's a square root there. Inside the dot product is dx over dt squared plus dy over dt squared and dz over dt squared dt. Okay? Yeah. Okay, that's a third look. Okay, the third kind of a formula for arc lengths. Okay, arc lengths. Okay. Now, as a matter of fact, in your first year, when you learn calculus, there must be a lecture on application of calculus, basic application of integrals. When you learn in that particular that lecture, I think you actually learned, you should have this one here. For a 2D curve, in that particular case for 2D curve, this is probably f equal to y of x, right? And let's say x is starting from A to B, okay? What is the arc length from A to B, right? For x goes from A to B. So remember, what's that formula? The s equal to, so A to B. Anybody still remember that? 1 plus? Yeah. Right? Okay? So if I change this one, f prime here, sometimes you write y prime, that's okay. Okay? Yeah? Was that right? That's what you learned in first year, right? Yeah. So, as a matter of fact, this is a special case of what this one is. It is a special case because it's 2D. We're looking at 3D here, right? Yeah. So, why is it a special case? So, if I have a curve y equal to f of x, okay, y equal to f of x. Now, from my previous lecture, what is the simplest solution, or what is the simplest solution for the parametric equation? If I want to parameterize this one here, okay? What's the simplest parametric equation for this one? What would you do to parameterize this? You would have said, remember in the previous lecture, what did I do? X equal to t, exactly. Y equal to this, right? That's the simplest way to parameterize it. Okay, so, but I said not necessarily you have to use a t, right? So if I don't use a t, I'm going to use what? S, or maybe, can I use x? I'll just use x, right? See that? Oh, x of course equal to x, and y equal to f of x, right? That's basically what it is. I didn't do anything, right? But that's a parametric equation. So now, if you substitute into this equation here, okay, sub this one here, guess what? You get this. Okay? So you basically change the t to what? T to x, right? What's dx over dx? It's 1. What's dy over dx? Sorry, I missed the square here, right? Yeah, so y prime squared. Okay? Does that make sense? Yeah. So, you do have a certain approach here in terms. It's also using slope. In that particular case, they use a slope to approximate to the segments, and then you derive this here. Okay, but what I'm trying to show you here is a special case. Okay, between these two. This is actually a quite famous equation. There's a lot of applications in terms of this arc length, though. Right. So let's look at an example. I'll give you a vector function for a arc, for curve. Okay. So this is a vector function over here. Okay, so vector function. Suppose that the t start at 0, okay, and I'll go to, in this case, I'll give you a pi here, okay. Maybe I'll try a slightly different. I'll use a t here. Basically, I'll use arbitrary here. Okay, arbitrary. So after a certain number of time, right? What will be the arc length? Okay, what will be the arc length? Okay. So first of all, okay, the parametric equation right here, or the vector function here. If you look at the vector function, well, what does this vector function represent? Circle, right? And the radius circle is 1, right? Okay. So we all know that the calculating the circle, the parameter, right? It's 2 pi r. That's how long it is for one run. So now we're looking at this, giving an arbitrary number of t. What's the arc length? Okay. So we'll use what we have derived here, okay, to do the calculation. So what do I need to do? I need to calculate dr over dt first, okay, and then calculate dot product. Okay. So dr over dt, okay. So this is dr over dt. So this is cosine t. That gives us negative sine 2t times 2. Okay. So negative sine 2t first, and then derivative of 2t give 2. So that's this. And this one is 2 cosine 2t g hat. Okay. Yeah. Okay. So then I'm going to calculate the dot product. Okay. The dot product, because that's part of the formula. Below the formula, there is this dr over dt dot itself, right? Dot itself. Okay. So that's actually pretty good because this is sine, this is cosine. When you calculating the dot product, so the square of this plus the square of this. So there is a 4 sine 2t squared plus 4 cosine 2t squared. So taking out of the 4, sine 2t squared plus cosine 2t squared is 1. So overall this is 4. Okay. So then square root of this, right, is what? It's 2, right? It's 2. Okay. Is that good? So now I'm ready for calculating the arc length. So arc length is the integral s. So the starting time is 0, and now the arbitrary time is t. So 0 to t integration of that. Okay. So s equal to 0 to t integrating what with what? With respect to this actually constant 2 here, right? And times dt. Okay. So it's constant. So this quantity here is constant. Okay. And apparently this is equal to 2t. Okay, 2t. So your arc length is 2t. Okay. Now let's check out a couple of special cases. At the t equal to pi. Okay. At the t equal to pi, what's the arc length? According to my calculation, it should be 2 pi. Right? It should be 2 pi. Okay. So if I go back to the circle here, go back to the circle. So when t goes from 0 to pi, when t goes to 0 to pi, imagine yourself there's a point moving on a circle. How much distance did the point move as t goes from 0 to pi? 2 pi, right? Basically, this is a circle here. As t goes from 0 to pi, the angle that the point moves is 2 pi. So basically, it moved 1 round around this circle here, right? 1 round here. It's a unit circle. And what's the what do you call that? Pardon me? Take my outskirt. What? Circumference. Yes. What's the circumference here? It's what? It's 2 pi r, right? Yeah, 2 pi r is 1 is 2 pi. Did we get 2 pi? Yes, right? We did get 2 pi. Okay? Yeah. Okay? So, that's a general formula for the arc length for a point moving along the circle, okay, with this parametric equation. Okay, so now remember in the previous lecture, I mentioned one concept. I said when you're deriving the parametric equation for a curve in 3D space, not necessarily you always have to use a t or time as a parameter for the vector function. You can also use what? You can also use this arc length as the parametric as a parameter, right? So for example here, this is what I derived for the s between s and a t. So guess what? This is basically means t equal to s over 2, right? T equal to s over 2. Okay? So then if I replace this t here with s over 2, I get an alternative vector function describing this circle, but this time it's in terms of the arc length now, right? So I will get r of s equal cosine s plus sine s g hat, right? So this is basically a parametric equation, okay, in arc length s, okay, in arc length s, okay. Because there are a lot of times there are a very subtle difference though, okay. If you remember, one of the things, okay, here's the parametric equation. Then what's the unit tangent vector? What's the unit tangent vector? So what would you do? The t hat equal dr over dt over what? Is this, right? Is this. And I did give you another formula in the previous lecture. This is the same as dr over ds. Okay? dr over ds. Okay? So if you have this guy here, okay, you can calculate t hat simply like this. But this one you have to normalize it, okay, after you calculate the derivative. Okay? Yeah. So in other words, this dr over dt, okay, not necessarily is the same as dr over ds. Okay. Yeah, just remember the difference. So many times it's easier to find r of t, not so easy to find r of s though. Okay, so was that okay? So that's basically So that's basically the application of the calculating arc length. So let me give you another one here for you to do. Actually, this is too easy. I'll skip this one here. Yeah. Is there any question for this one? Arc length? Okay. So I'll jump to the next points. Okay. Yeah. So what we actually more interested in the next topic though. Okay. It's what we call the line integral. Okay, line integral. So I call it line integral. Okay, more precisely, it's called scalar line integral. This is a little bit a disruption of the order of the textbook. Generally, this was left in the textbook in the chapter 16 when we start to deal with integrals of vector function. Okay. In the vector fields, okay, so in the later parts, but I feel this is kind of quite a natural evolution from this arc length to this scalar line integral. Okay, so this is why I put it over here. Okay. Yeah. Okay, so what's the scalar line integrals? I'll start with a sort of a more practical question here. Okay. Okay, so let's just see, or look at the planar case. I find a wire, okay, or a straight rod. I'm going to place that rod along the x-axis. Okay, so this is the rod. okay, goes from x equal to a to x equal to b. Now I'm more interested is what's the mass of this rod, okay, given that the density of the rod is rho of x, okay, and then what's the mass of this guy here, right? Yeah, this is another application you learned in the first year regarding integrals, okay? Yeah. So how you proceed with this kind of question in the first year, this is what happens. You take a very small segment at here. Okay? So let's say this small segment you're taking is at x of k location, okay? X of k location. And if that small segment has a very small mass, we call it delta mk. Okay? Yeah. So essentially, what we're doing is we're separating the rod into many small segments, and each segment has a small mass delta mk. And then we're going to add them up, and that's the total mass of this rod, right? Yeah, that's the idea. Okay. So if we do this, so that means, okay. So that means what? That means, okay, we are going to calculate like this. So delta mk, okay, delta mk for this mass here, what does that equal to? Because this is a pretty small segment, so at this small segment, we can consider the density root of x. It doesn't change. It's approximately the same at around this location. So that equal to rho around which location at around this x of k location, right? X of k location. Times, so this is a thin rod, so this is the density times this length at here, right? Times the length. And the length is the delta x of k, okay? So very small segment around the x of k location. That's the mass at this location, okay? Then the total rod mass, okay, is the summation of many of this. So I'm going to be summated here. Let's just say I have n number of segments at here. So I'm adding n number for this, okay? Adding n number of this, right? That'll give us the total mass, okay, for the rod, okay? And then back to the concept of a limit, and back to the concept of basic derivative of integral. If I let n go to infinite, right? So if you have n infinite number of segments along the rod here, then the mass becomes basically the summation sign, the discrete summation sign becomes what? Integral, right? Becomes integral. Okay? Yeah. So this time you're going to integrate from a to b now, and this rho, this is a density function rho of x, and delta, right? Delta becomes d, so that's a dx, right? Dx here. Okay, so this is basically how you get the mass of the rod, okay, for a very simple case, right? Using this approximating process. Okay. So now same question comes to this 3D now. Okay, same question comes to 3D. So what if we're looking at, it's not a rod in 2D, it's not a straight rod, it's actually a curve in 3D space, right? So what if a 3D curve, right? And what's the mass of that? Okay, what's the mass of that? Okay, yeah. And so I'm just draw a similar diagram here. So let's say I have a curve in 3D. Okay, curve in 3D. And I'm looking for the mass of this curve. Okay, looking for the mass of the curve. As usual, if you're given a curve, then you must be given, okay, a vector function describing, okay, this curve, right? Vector function describing this curve. Okay, R of t. Suppose that it's starting with t equal to a and t equal to b, like this, okay, for this curve. Okay. Yeah. So this is a y in 3D space. What we also need is a density, just like the planar case. So we also need the density of this curve, right? Yeah. Assuming a non-constant density. So we're going to let, okay, f of x, y, z, okay, as the density, okay, of the wire. Okay. So now this is where I often find people having a little confusion right here. What exactly is f of x, y, z? Physically, what does that mean? So physically, you look at this one, f, this is a scalar function first of all, okay? If you plug in a value x, y, z, you get a value out of this expression, function f, okay? So we're looking at, for this one here, it's a specific set to describe the density of the wire. Basically, if you point to a location on a wire, let's say this is location P at here, and there's a coordinate set here, right? This coordinate. Then you plug the coordinates back here, that give you a density at the location, right? So given different locations, you get a different densities. You know, somewhere is more dense, somewhere is less dense. Okay, so that's basically the idea. And of course, you say, oh, can I plug a point somewhere along here? Yes, you can, but that doesn't make any sense anymore because that one here describes, only makes sense along the curve here because that's where we're interested. All right? Yeah. Okay. Okay. So I'll just write down. So I need to show you something later, so that's why there's something down there. So I'll just write down the curve C's vector function. Okay, to be more. Okay, and T, okay, between A and B. Okay, yeah, just an A and B. So that's how. If you're more precise, maybe you should write A to B. So that indicate the direction of this T, the change of the T there, right? Change the T. Okay. So now, if we say what's the mass of this one here, so what we can do is this: we can do a similar approach as the raw there. So I'm going to take, okay, I'm going to take a very small segment along this curve here, okay, very small segment. So I'm going to call this small segment. This is maybe a segment taking at a t equal to tk time, right? Maybe it's taking at this location, okay? And basically, for that point, I get x of tk, y of tk, and z of tk. Okay, so for that at that moment, that's the coordinate. Okay, that's the position. Okay. And this is very small, so I'm going to call that delta sk. Okay, so the arc length for that particular segment is delta sk. Okay. Yeah. Okay, so then what would be the mass for this small segment then? So the mass for this delta sk would be what? This is the density function right here. Okay. Sometimes lost some down, right? This is a density function. Okay, and this is the small segment right here. So as the previous case, we can assume that the density is constant within here, right? Within here. Yeah. So the density will be basically, for that delta mk, is the density at which location? At this location. The density at this location, okay? At a small segment, so there's a constant density around here. So the mass will be the density times the length, and the length right here is delta sk. Okay? Does that make sense? Yeah. That's the mass for that particular segment. And if we're looking for the total mass of the wire, so what do? We suppose that we have how many? We have maybe n number of them. So that meaning the total mass is going to be a summation, n from 1, not n from k from 1 to n, right? The n number of segments along the wire, and basically add all of this up, right? Basically add all of this up. So delta mk, okay? Delta mk. And that equal to n at here, k equal to 1 here, alpha for this whole bunch, and delta sk. Okay? That's the total mass, or approximation, right, for the total mass. Okay? Approximation. Okay? Then, as n goes to infinite, okay, consider yourself the infinite number of segments along the wire, then this summation becomes integration. Okay, integration. And this time we're integrating, right? We're integrating along the curve C. Okay, we're integrating along the curve C. What are we integrating? We're integrating this function f. Okay, this function f. So instead of a t key now, we can just use x, y, z. Okay, x, y, z. Okay, and this delta sign becomes d, so ds. Okay, ds. Okay, now this is basically what we're looking for here. This is what we call a line integral. Okay, it's an integration along a line. Well, so this is the name here. It's not really along a line. It's actually along a curve, right? So technically speaking, probably should be called curve integral. But somehow it has been everybody calling it a line integral here. Okay, so it's not really integrating along a line. It's along a curve. So this one here is this so-called a scalar, okay, line, okay, integral. Now, what does that mean? This scalar here refer to, okay, so the scalar here refer to actually this function, okay, because this is scalar function, okay, as in our future lectures, you will see that there is a so-called vector line integral. Okay, so this can be vector, and line at here, okay, refer to this c. Okay, refer to this c here. Okay, and you can draw a better one here. The line refer to this c here. Okay. So that's where the name is from. Okay, and integral, of course, this integral. Okay, so. Looking at this one here, how do we proceed, right? We need a workable formula. But you have x, y, you have a s. Apparently, you can't do anything at this stage yet. But we have just derived what? ds. What is ds then? Good, right? This is a ds we derived. Infinitesimal small segment or arc length, this is ds. So I'm going to basically plug this into the formula that we just derived. Okay? So I'm going to plug it over here. At the same time, this x, y, z, okay, this x, y, z, remember, what does f here represent? Represent what? Density, right? It's a density along where? Along the wire. So, are you looking at any x, y, z other than the location on the wire? No. So this x, y, z is restricted to the location on the wire. And what describes the wire? Right? So all you need to do is replace this x, y, z with x of t, y of t, and a z of t. Okay? So now you have a new formula, which is integration along the curve C, f, x of t, y of t, and z of t. ds is that formula we just derived. Okay, there we go. That's the line integral here. Okay, that's the line integral. Where is x of t, y of t, z of t from? It's from the vector function for the curve. Okay. Now you probably wonder, what is f then? Yeah, the question didn't. This is a general formula. Once we have a specific question, then we will know what expression for this f is. Right? You will have this. Okay. Yeah. Does that make sense? Okay. So understand the meaning behind this one here. Now, however, I do need to mention though, I derive this one using the so-called mass of a wire. But, if I go coming back to this formula here, okay, coming back to this one here, this line integral formula, that doesn't necessarily always refer to the mass of something. And it could mathematically just pure math. And this one maybe represents some other physical quantity, right? You never know, okay? Maybe this one represents temperature distribution along the wire, okay? Yeah. So just remember, the end results here is a general formula, okay? Yeah. Okay, so now let's look at a couple of examples here, okay? I'll give you the first example is integrate this function integrate this function over a curve C, okay? And this curve C, I didn't tell you, but it shows you it here. So the curve C is a straight line between 2 points. One is origin, and the other is a 1, 1, 1. Okay, this is a C curve here. Okay? So the question didn't tell you the parametric equation or the vector function representing this curve C. So then what do we have to do? We have to basically derive the parametric equation for this curve C first, right? Yeah. So essentially, what is the parametric equation? What is the function, vector function representing this curve C, right? Okay? And this is a function. You integrate this function over this curve C. In other words, this x, y, z here will only change along the curve C. Okay? Yeah. So what's the curve C equation, parametric equation? It's from 0 to 1, 1, 1. What would be a possible solution? Exactly. So t, t, t. T, 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 but what's the range of T based on the given coordinates? 0 to 1, exactly, right? So double check, does that make sense? If I sub the T equal to 0 here, 0, 0, 0, that's where it starts, right? If I sub the T equal to 1 here, 1, 1, 1, that's where it ends. That's great, right? That's great. But of course, you might, does that really describe a line though, right? Does that really describe the line? Well, if this is a line here, and then when you project to each one, each one of the plane in here, it must be a line, right? So when you project over here, what's this line? This is basically y equal to x. Okay? When you project to the other plane, you get z equal to x. When you project to here, you get z equal to y, and you get z equal to x here, right? Yeah. So t, that essentially what happens here. Okay. Alright, so now we're ready for integration for the line integral. So the question basically is integration along the C with respect to this function over which one? Over the C here. So C, so dr over dt dot dr over dt and dt. But this is where you gotta be careful now. When you integrate, okay, this f here, okay, I'm gonna rewrite this one, write this one first, write it down this one first. This one here, you don't integrate anywhere else other than along the curve C. So I'm gonna, this is my vector, this is my function f here. So I'm going to replace the x, y, z here with what? X of t, which is t. Y with y of t, which is t, and z with another t, right? Now this is very, very important because if you don't do this step right, everything else will be wrong, right? So you got to know what are you replacing with here, okay? Yeah. So I'll maybe use a red here. This is x of t, so that's going to be moved here. This is y of t, that's going to be replaced here, and this is a z of t, and that's going to be for this guy here, right? Yeah. So then essentially I will get, okay, the function we're integrating with, we got a t minus 3t squared plus t, okay, plus t. Okay, that's what this function becomes. And of course that equal to 2t minus 3t squared. Okay. Okay. So now once we figure this out, we can continue on that integral here. So then you probably want to calculate dr over dt first, right? Before you move on here. So dr over dt. So instead of writing everything all in one shot, write all those elements out, components, right? dr over dt, what's the r? This is r here. When you take this derivative this way here, this is actually give you, what does that give you? 1, 1, 1, right? 1, 1, okay? And dot product, okay? That give you dot product 1 plus 1 plus 1, 3, right? 3. So this whole integral here, right? This whole integral here, if we now we are able to fill out all the blanks. So this whole integral, what are we integrating? We're integrating this function, which is 2t minus 3t squared, right? And this square root, it's a square root 3, okay? Square root of 3. And dt, okay, dt. And then what will be the integral limits then? Is between 0 to 1, okay? Yeah, 0 to 1. Okay. So you look at this integral, that's not strange, right? That's pretty straightforward, okay? So you can carry out this integral no problem at all, okay? Yeah?
What happens if all the points are at 1? Like, what would your integral limits be?
Come again? What happens when all the points at 1?
If they aren't at 1, so say it was like 1, 2, 3, what would your limit be for your integral?
Oh, I see. So you mean you have some other locations, right? Yeah, that's actually the next question you'll see. You will have the line integral here. You'll integrate separately. Integral is a C1 first, integral with a C2 first, and you add them up. Yeah, that's the next one. I'll show you what it is. Okay? Yeah. So can you calculate this one here? Yeah, just do a quick calculation. So what does this result give you? It shouldn't take you more than 1 second, huh? More than 1 minute to that's too much. What do you get? You got 0, right? Yeah. Okay, so I think that some of you immediate question, 0, what exactly does that mean? I got a mass of 0, right? Yeah, in this case you got a mass of 0. But in this case you actually don't need to think of it as a mass, okay? This is just a pure mass calculation here, okay? It probably doesn't carry any physical meaning at all, okay? Yeah. So just somehow it's a 0. You could have got a negative, who knows, right? Okay? So now let's look at the next one here, as one of the students pointed out here. So I'll give you another example. This one we actually have seen it in my previous lecture. I have this curve like this. So this is C1, this is C2. Okay? So C1 goes from origin to 1, 1, 0. C2 goes from 1, 1, 0 to 1, 1, 1. Remember this example in my lecture, right? what we did is we derived the parametric equation for C1 and C2. Okay? Yeah. So let's do the same thing. Suppose that I want to integrate the same function f of x, y as the previous example. Okay? So x minus 3y squared plus z. Integrate this guy along this curve C1 and C2. Okay? C1 and C2. So basically we can consider C1, C2 as the same. This is a formula. If you have a C, which is a C1 plus C2, all you need to do is you integrate C1 and C2 separately, okay, and then you add them up. Okay. Yeah. If you have multiple more than 2, and then you just keep adding. Okay. Is that good? Yeah. So I guess the question actually, once you know this one now, the whole thing boils down to what would be the parametric equation for C1, what would be the parametric equation for C2, and then you substitute into the formula as in the previous example, and then you do it, right? That's essentially the procedure. Okay? Yeah. Okay, so I'll write down the C1, C2, and just to jog your mind, if you remember this, for C1, the parametric equation, let's use R1 in here. Okay, R1. So tell me, do you remember what this one is? Or what would be a candidate for this parametric equation for C1? T, 0. And this is t goes from 0 to 1, right? Okay. And the parametric equation for C2. Okay. So here to here, what would be a candidate? 0, 0, t. And t goes from 0 to 1. Yeah. And you should stop writing 0, 0, t. This is not right. What should that be? 1, 1 t, yeah. So remember, this represents the coordinates of the points on the curve. Does this coordinate, pick a point, is x 0, y 0? No, right? What's the x here? 1. What's the y here? 1. Okay? Yeah. Trust me, this simple mistake will cost you dearly in this kind of question. Because why? This is the first step, right? Guess what? You go all wrong in the next thing here, okay? And I'm not sure from which year, but I've been hearing feedback. This instructor is very rigid in the marking. I don't get any partial marks. You do get partial marks, but just when you make this kind of mistake right from the beginning, it will be very difficult to get partial marks, right? Yeah. So don't make that mistake. Okay. So once you get C1, C2 now, right? So let's calculate the line integral along. So let's calculate each one here, okay? So what's the line integral along the C1 first? Okay. This is the line integral along the C1. Let's just see what calculation do we need to do before we plug in all those numbers here. So I'll write it separately. So f x, y, z, okay, f, x, y, z. F, x, y, z needs to be replaced, the x, y, z needs to be replaced with what? With x of t, y of t, z of t. With which x of t? With this guy, right? From the C1 here. So x of t in this case is t, y of t is t, and z is 0. So for this C1 here, that's x minus 3 minus 3 squared, okay? So t minus 3t squared plus 0, right? So t minus 3t squared, okay? That's the f function along C1, okay? Along C1. And then dr over dt, okay, that's easy, that's 1, 1, 0, okay? 1, 1, 0. Okay. So once you have these two now, we can simply plug into the formula that we used in the previous example. Okay. So So I'll just write the integral here. This is t minus 3t squared. That's this function. And ds is a square root of dot product of this. Dot product of this is 1 plus 1 is 2. Square root is square root of 2. And then dt. And the range of the t, as you put it down here, is from 0 to 1. Right? 0 to 1. So that's the integral, okay? Line integral along C1. Okay? Along C1. Was that good? Yeah. So, next, integral along C2. Okay? Integral along C2. I'll just write this. Along C2, first of all, this function f of x, y, z, what would that be? So function f of x, y, z, you replace this x, y, z with x of t, y of t, and z of t, which means it's 1 minus 3 plus t, right? So remember what I said, if you put a 0, 0 here, then the function f won't be right, when you replace with the x of t. So 1 minus 3 plus a t, so which is t minus 2, okay? T minus 2. And dr2 over dt, okay? dr2 over dt. So it's 1, 1t, so derivative 0, 0, 1, okay? 0, 0, 1. Okay. And then along the C2, right? Along the C2, we're integrating with the t minus 2, and dot product of this is 1, square root of 1 is 1, so dt. We're integrating from 0 to 1. There we go, right? That's the second line integral, okay? So you have this, and both of them are pretty straightforward, right? There's no sine, cosine. A lot of time I find when trigonometry is involved, integral is difficult. But this is pretty simple, so you can try it out. Yeah. Okay, I think this one you get this, and this one you get this. Okay? Yeah. This. Yeah.
Just for the balance, is there ever like a time where like
not one?
The integral would be different? Like,
you mean not one here?
Yeah.
Well, of course. Well, let's just see, right? The parametric equation, this is 1, 1t. So what if somebody says, this is 1, 1, 2t? What will be the range of t now? 0 to 1/2, right? Exactly. Okay? So that your integral limits will be from 0 to 1/2.
What if, like, do you ever have it where, like, there's a bunch of different t's in there? Like, it'd be like 3t and 2t.
Oh, you mean 3t here?
Like it's a curve. Like it's a curve.
Oh yeah, sure. That's purely based on, it depends on what kind of a curve that you have it here, right? You know, maybe I'll say, okay, the first portion of the curve, maybe let's just say, maybe the first portion is this. Okay? Yeah. What's this? Maybe this is y equal to x squared. Okay? Yeah. Or maybe the first portion of the curve is this. Now what's this guy? This is actually maybe half a circle, right? Yeah. So yeah, it purely depends on the curve, and also depends on how the curve is drawn, and you need to come up with a appropriate parametric equation for that curve. Make sense? Yeah. Yeah, you'll get to some more exercise for this kind of homework. You'll see a different kind of line integrals, okay, with respect to different curves. Okay, so was this answer right? Yeah? Anybody check it out? Yeah? Okay. So anyway, a lot of times you have to carry out integrals here, okay? Yeah. Okay, so I'll make use of the last maybe 5 or 10 minutes here just to go ahead and then talk a little bit more on a new topic now. Okay, but I'm going to kind of get away from vector temporarily, go into this function, okay, scalar case. Okay. So this is another topic. This is basically starting off with a slightly different topic. We call that multivariable function. Okay, so not just multivariable function, and we're also looking at their operations. You know, just like vector function operation, meaning how do we carry out the derivative? How do we calculate integrals? What are the meaning behind the derivative? Okay, and things like that. Okay. So multivariable functions and then their operations. Just looking at the name multivariable, okay, that kind of differentiates from what you learned in the first year. What we learned in the first year essentially is always a function of one variable, f of y equal to f of x. So this is what we call scalar function, right? Scalar function. Okay. Now, more interesting is you're going to look at the multivariable function, and that's the kind of function referred to this kind of case. W equal to f of x1, x2, okay, up to maybe x of n, okay, xn. So that's the loc of a multivariable function. Okay. Now, if I give it a proper definition, okay. So basically, okay, you have you basically have a set D, right, which is a so-called n-tube. Okay, so it's x1, x2, and xn. Okay, yeah. So that's sort of like what we call a dimension. So you have this set D, n-tube. There's basically like a vector of n dimensions here. Okay, a vector of n dimensions. Okay. And the W, okay, happen to be a function of this n-tube vector or n-tube dimension x1, x2, and xn. Okay, yeah, that's more. It's not rigorous, right? But you know, more wording is needed. But that's basically what the multivariable functions is defined. Okay. You actually have seen multivariable function probably quite a bit in real life. So, for example, we're saying what's the temperature, okay, inside this room here at any location, right? So what do you do? You basically you have these coordinates of a certain point in this room. You plug it into a certain function, you get the temperature, right? Yeah. So the first step, what we want to do is, okay, I need you to understand a couple of things, very simple things, before we move on at here. Okay. Yeah. So I'll give you two things that are here. One is, as before, we said there's ax plus by plus cz equal to d. Okay. What does this represent? What does this represent? It's a plane, right? Okay. Okay. If I describe this more precisely, and I guess I would describe this as what? I would describe it as a so-called equation, right? It's an equation. So you have equation is there are two sides of the equal sign, okay? Equation. Now, if I rewrite this one here again, if I rewrite it as z equal to this 1 over c and d minus ax minus by. Okay, if I rewrite this, and I didn't change anything, right? Just rewriting it. Okay. Yeah. Now this one is actually becomes what? This is exactly in the format that we just introduced. This is a multivariable function, right? So this one essentially is a multivariable function. A function of what? A function of x and y. Okay? See the meaning in here? Okay? Is there any story you guys want to share over there? Sounds looking like a pretty funny story, huh? Yeah? I need a dose of that, at this time of hour. So, anyway, let's continue here. Okay. So, what I'm trying to say is, okay, often in time, you need to be aware of the difference between an equation and a function. Okay, so a function can be derived directly from an equation. All right? Yeah. So the next point I want to make is particularly for a z equal to f of x, y. This kind of a case here. This is what we call it's a visualizable, in 3D space. Because why? You see, if I plug in an x and y value, what do I get? I get a z value here, right? So imagine this. I have x, y value here, and then I get a z. And then another x, y, I got another z. So if you connect all together, imagine what do you get? You get a surface, right? You get a surface. So this one here, we can visualize that. Okay, visualize that. Okay, so that's what a general magnetic step. I want to show you a couple of interesting ones. Okay, to get some ideas of what they are. Okay, so but you need to know though. Okay, if you have a W is x, y, z like this. Okay. That you can sketch it in 3D space. Okay? You can't. Okay? So here's a couple of things here. So z equal to this, and what we just said is a plane, right? It's a plane. So if I use z equal to negative y, guess what I get? I get a plane here. Okay, I get a plane. You can try the Maple command and also upload a set of them and you can also try them out. Okay? But it doesn't matter what, z equal, but however, if you just look at z equal to negative y, what does this represent actually? Forget about 3D. What z equal to negative y represent? It's a straight line, right? It's a straight line in which plane? The z, y plane, okay? Yeah. And if you have this kind of equation, x squared over a squared plus y squared this minus z squared over this equal to 1, plugging certain a, b, c, this is what we call one-shaded hyperboloid. Okay, so this is the shape like this. Okay, and actually you see a lot here. This is the power station cooling tower. Okay, that's the shape of that. And if you have this one here, z equal to this, that's called elliptic paraboloid. And this is a general base. This is like a bowl here. Okay, a bowl. If I draw this, z equal to 1 minus x squared minus this, this is actually an inverted bowl. Okay. Yeah. And this one here, okay, this is called hyperbolic paraboloid. This one, okay. In a lot of time, it's called saddle. So like a saddle for a horse, okay. And you know what this is. Now, why is it called a saddle? Because when you look at this one, this location here, okay, this location, as you're walking at this location. If you take a derivative in the next, we'll see that the derivative is 0. Basically, what we call it stationary point. However, if you walk in this direction, it's increasing. If you walk in this direction, it's what? Decreasing. That's a saddle. Okay? Yeah. So just like in 2D, we have a so-called point called deflection point. Okay? Yeah, it's basically this. And then in the end, we have this one here. Okay? And that's called implicit equation, okay? Because this is not in the z of this. And funny one is it draws this one. So if you're having a Valentine Day, you can give this one to your special, okay? And just to impress her. And actually, this equation has a very interesting name. This is called sextic equation, okay? Yeah, I didn't make it up. It is called this equation. So you have a constant equation, linear equation, and others. Okay. Yeah. Okay. Any questions? Good.